switching out laptops. Sorry. Yes.
particular, I'd like to stress that I'm referring to cryptocurrencies in general, because our attack applies to a wide class of cryptocurrencies, not just Bitcoin, although for our examples we'll focus mostly on Bitcoin. And the problem is one that is a very pressing one and an important one, and that's Alice wants to buy a cookie. And she wants to pay for that cookie. And in particular, she wants to buy this on a website. So we're all familiar with this. We probably do it many times a day. And go to Amazon, we go to the product page, pick the cookie we like, add it to our cart. When we're done shopping, maybe we get some milk as well, and then we add that to our cart. Our cart page usually gives us a preliminary total, which doesn't include, say, shipping prices and the like, and taxes. And then when we're done, we go to the checkout page. And in the usual web payment scenario, where you say you're paying with a credit card, the checkout page is sort of the last step. You put your credit card details in, you see the final price, and you're done. However, when you're paying with a cryptocurrency, on the checkout page, you indicate that you'd like to pay with a cryptocurrency, and then you're forwarded to a payment processor, which says, okay, here's the address, send us your payment, and then only once the payment is received do you go to the final receipt page. And a payment processor looks like this. This is BitPay, the largest payment processor, and they throw up something on your screen that says, here's the Bitcoin price, because notice when you're shopping, you may have been shown a fiat price, such as a USD or euros, but on this page, they'll actually do the exchange rate and tell you to send exactly this many Bitcoin to this address, and you have a 15-minute time window, which is your time to make the payment, and after that, it expires. So, okay, Alice wants to buy a cookie. She now has some idea how, after seeing that tutorial, so she goes ahead. It's a very expensive cookie. It costs 8 Bitcoins. But it's really, really good. So in Alice's wallet, she has these 3 coins. She has a 5 coin, a 3 Bitcoin, and a 6 Bitcoin coin. And these are Bitcoin outputs, but think of them as each of these are controlled by a different public key. And on the blockchain, there's no way to know that that these all belong to Alice, but she owns all these because she has 3 public keys, and each one has this amount associated with it. And Alice was really, really good in her math class, and she knew that no problem, she can put these 2 in and get her 8 Bitcoin. Awesome. And notice that she has 2 inputs from a single transaction, 2 different coins, and this leads to linking, because now anyone that sees this transaction on the blockchain can say, okay, these 2 coins are controlled by Alice, or by the same person. They may not know it's Alice. And in particular, they can say any other coins held by those same addresses are also held by the same entity. So we've clustered addresses in this way, and this can be done transitively to build up large clusters. And this is an idea going back to 2011 and the well-known work by Sarah Meiklejohn. Is expanded on this and give other heuristics, but for our purposes, let's just think of clustering as a black box. One of the things that it uses is this shared spending heuristic. Okay, so how does clustering work? So you have all these coins that are not clearly associated with each other, and then you run your nifty clustering algorithm, and boom, all the coins get colored. Which tells you that there's some shared spending among them, and you can cluster them and say, okay, these coins are controlled by similar entity, by one entity. So each of these clusters represents one logical entity, even though each of these coins may be from a different address, but now you know that these addresses are controlled by a single entity. Okay, so how do you what's one heuristic that's common to great clustering? You use what's known as mixing. And here we're looking at decentralized mixing, which is CoinJoin. And the basic idea is very simple. You have here 4 people getting together, each of them have clusters of addresses, and they create jointly a single transaction in which they each input a coin and output a new coin to a fresh address. And in particular, these fresh addresses, there's no way for someone looking to correlate the output address to the input address. So now, all of these people coming out have an anonymity set of 4. Because you know that it's one of these inputs corresponds to each output, but you don't know which one. And you can do this in rounds, and you can get a large anonymity set of many coins that it's not clear which coin is actually belongs to you. Okay, and this leads us to our first attack, which is a single transaction linkage attack. So Alice wants to buy a cookie. She's getting there. She has a cluster of coins. So what does she do? She goes ahead and sends one of her coins to the shop. And the shop goes back and sends the cookie. And everyone's happy, except shop can now say, well, I saw this coin, and I know that these coins are all clustered, so this whole cluster belongs to Alice. So shop identified Alice. Okay, that's clear that can happen. But the question that we ask, one of the questions we ask in this paper is, what can a third-party tracker sitting on the shop's website identify about Alice? Now, clearly, if the tracker sees everything and sees the Bitcoin payment address, it can go ahead and say, well, this is Alice's transaction, and do the clustering itself. So if it has the same information as the merchant, there's nothing interesting here. But the interesting question is, in cases of uncertainty, where the tracker doesn't have the payment address, maybe it has the fiat payment. Maybe it has just the payment price. Maybe it doesn't even have the full price. Maybe there's price uncertainty, so the tracker sits on the cart page. It doesn't know shipping, if there's shipping or no shipping, or what the tax was, and so we modeled price uncertainty by giving a small number of fixed value samples from actual shipping rates that we did in our crawl, which I'll describe later, and always including 0 because 0 represents free shipping. And this is how we modeled price uncertainty. And then there's exchange rate uncertainty. So anyone can go and take a look at any given second what the exchange rate is, and that's pretty clear and straightforward. But the question is, I don't know the exact second that the exchange rate was computed. Maybe, you know, and within a few seconds or minutes even, this can be very volatile. So, and the third level of uncertainty is payment time uncertainty. You know that Alice is going to send the payment to the blockchain within these 15 minutes, but or you don't know exactly when it is. Maybe it's 15 minutes. Maybe you have some better idea. So depending on the information that the tracker can see, there's lots of different places for uncertainty. Some trackers will have more, some will have less, but I'll omit the details for that for now. Anyway, in our paper, so we tried to estimate this linkability, and we used BlockSci to simulate 10,000 payment flows. And we modeled uncertainty in this way, and in this example, this is our default parameters where the price uncertainty set is 5, meaning you know that it's one of 5 prices based on, say, the shipping prices that the vendor offers. You know that the exchange rate window, you're assuming that it's a 5-minute window, and you're assuming that the customer will pay in a 15-minute payment window. And we found, under these conditions, about 62% of the time, the anonymity set is 1. What does that mean? It means if the tracker were to look on the blockchain with all these parameters for all the transactions that meet these criteria, there's exactly 1 transaction, and it will be unique, which means that the tracker, even with partial information, the tracker doesn't have the Bitcoin address, the tracker doesn't have Alice's, the exact Bitcoin payment price even, but the tracker can identify the transaction with its limited information. With that, we'll build on this to our cluster intersection attack. And again, Alice really, really wants this cookie, but she's smart. She doesn't want to be identified, so first she mixes a coin with CoinJoin. And now she gets a beautiful, freshly mixed coin, and she goes ahead and sends that to Shop. And Shop sends back the cookie, and now Shop can't identify the cluster because the coin is mixed. It knows that there's an anonymity set associated with it. Here, we'll assume there's only 1 round of mixing, so it knows Alice is one of these clusters, but it doesn't know which. Okay. And now Alice wants to go ahead and buy some milk, so she goes to a different shop, the milk store, and does the same thing. She mixes coins with a different set of participants, and great. She has a freshly mixed coin, sends it to Shop, Shop sends back some milk, and Shop 2 doesn't either know Alice's cluster. Now, what Shop 2 does know, that again, there's an anonymity set associated with it. It's one of these 4 clusters, but it can't identify Alice. And again, if in practice you do many rounds of mixing, it won't really be an anonymity set of size 4. It will be much, much larger. Great. But what about a tracker present on both Shop 1 and Shop 2 site? And so Shop 1's view is these 4 clusters, Shop 2's view is these 4 clusters, and notice that there's one thing in common. The intersection is exactly that cluster. So Shop 2, sitting on both these sites and knowing, well, Alice made a purchase here and a purchase there, can do the intersection attack and say, great, this is exactly Alice's cluster. And intersection attacks have been presented in the communications literature, but we show that this is very, very practical in cryptocurrencies as well. And we did a large-scale measurement where we first identified real CoinJoin attacks on the blockchain, and then we simulated a victim who mixes for up to 5 rounds, and we picked a timestamp, found the real CoinJoin attack on the blockchain, and simulated a victim mixing their coins in that way. And then we posited an adversary who knows that two of these coins were actually belonging to the same person. And we said, well, what can that adversary learn? Can it re-identify the cluster? And again, I'm just going to give a small sample of our results, but we found that the cluster intersection attack is very effective. As would be expected, with the number of rounds of mixing, it degrades. And it was also be expected, with the more observations you have, it improves. So the intersection of two different payment addresses would be smaller, but the intersection, if the tracker knows that, say, Alice has 3, 4, or 5 purchases, the intersection is likely, smaller and has a much larger chance of being unique. Finally, we did a web measurement, and we said, well, what can trackers actually see on Bitcoin pages? And we had some pretty astounding findings. The very top-level view of is that 40% of trackers leaked transaction-relevant data to third parties. 41% of top-level sites leaked transaction relevant details to third parties that would help them identify transactions on the blockchain, and 35% leaked PII. And notice that the PII leak doesn't have to happen on the same website. If there's a third site in which Alice paid with just a credit card, but she used, but that site sent some PII to the third party, and the third party can use that to tag it with Alice's address, assuming it has a cookie on each of these sites. And we used OpenWPM for our web measurements. Finally, we did an end-to-end measurement where we actually participated in we simulated a wallet that started off with, well, we took a real wallet where had real spending patterns that the coins were clustered by our clustering algorithm, and we went ahead and participated in coin joins to mix these coins. And we went to 20 different sites, and we made purchases at these sites, and we looked at what trackers were on each site, and in particular, we looked for overlap in trackers that could see 2 of them, and we found that there were 25 pairs of sites in which 2 trackers overlapped, and under conservative assumptions, in 80% of those sites, the trackers could our attack worked end-to-end. So first, that they can use their partial information to identify the payment transactions, and second, once they identify the payment transactions, they can successfully perform the cluster interception attack, leading back to Alice's cluster. Mitigations, what are mitigations for these attacks? Well, there are merchant-level mitigations, which basically amounts to stop sharing so much data with trackers. Unfortunately, as we show in our paper, a lot of these sharings are intentional. And we derive that based on how they're shared. If they're shared in the body of, say, post addresses, they'd be, a post request, they'd be intentional, as opposed to in a referral request, they would be unintentional. We found that most are intentional, and this is expected because these tracking relationships are very profitable for merchants, such as retargeting. So the best defense for users is self-defense. That is, increased rounds of mixing. So we simulated up to 5, and we saw the attack degrade, but likely if you did more rounds of mixing, assuming that the number of observations are small, the attack would not be as successful. Tracking protection, such as Ghost3 or AdBlock Plus, that helps a bit. We reran the attacks with tracking protection now, and we found there were still leaks, but less. And of course, you can use different payment methods, such as anonymous cryptocurrencies, that will this attack should not apply to. Thank you very much for listening. In conclusion, I'd just like to say, payments in cryptocurrencies are a hard thing to get right. Cryptocurrency payments privacy sort of merges the bad parts of data anonymization, where you have a large trove of data that needs to be kept private, as well as payment problems that we see in communication networks, where you can analyze access patterns to learn potential linkages between different payments and addresses. And again, this work applies to both Bitcoin as well as any other standard blockchain-based cryptocurrency without privacy overlay. Thank you very much for listening. I'm happy to take questions.
Thank you, Stephen, for leaving time for one question.
Good talk. As far as I saw, you mainly looked at identifying people as a binary metric. So if the intersection was 1, then you found the right person, and if not, then not. Did you also look in how much is the anonymity set decreased if you could not identify one single person? Like, for example, if it could have been 2, like, do you have any intuition on how much you decreased the number of possible persons that could have spent a coin?
Yes, so in the paper we gave the full results, and we sort of posit an adversary that it's not really a binary adversary. The adversary we posit tries to identify a single, but then if it identifies 2, it just takes sort of a random guess. And so we found that slide that I showed, there was a 62% positive rate of getting a single transaction, but we found an adversary behaving like this that tries to be unique, but otherwise uses takes a guess of the other ones, has a 76% rate, so it does improve. And in particular, I'd also like to say our assumptions were very, very conservative. Oftentimes, an adversary a tracker is sort of embedded directly on the receipt page. So it knows right when that redirect happens, it knows exactly when the payment happens. So in practice, the trackers often have much more information, which will allow the identity to be higher as well.
Thanks.
Thank you, Steve. So now, time for some good news for
So I'm presenting a solution called Mobius, which is a tumbler for Ethereum. So this is introduced very nicely by the previous work because this is a way to make tumbling and like mixing more frictionless, so that these intersection attacks would like have to work over a large range. So to introduce the problem, Bitcoin, as we know, isn't very anonymous. Like very easily you can track money through the ledger, and this is how clustering attacks work. So you can see there's these like very obvious links between sender and recipients in this case. So everyone knows that Bitcoin isn't private, so what is privacy is the like next question that we would want to ask. So we have different notions of privacy. So for a single transaction, we would have sender anonymity, which means that the recipients in question don't know which blockchain address corresponds to their specific sender, which would be the case if you use this naive solution of using this like ideal trusted tumbler that sits in the middle, that is here represented as the Bitcoin bath. And the way that this solution would work is that Charlie and Alice, wanting to send money to Dora and Bob, would just give the money to this Bitcoin bath and give the addresses that they know correspond to their intended recipients. So Charlie would give Bob's, Alice would give Dora's, and then the Bitcoin bath would mix together all of the money and then send it on to the intended recipients, severing the link between the sender and recipient. So then we also have receiver anonymity, which means that the senders can't determine which receiver is their intended receiver. They can just see, they know that the receiver that they desire to withdraw the money will get the money, but they can't find that mapping between the person that they know they're sending money to and the actual address on the blockchain. And this means, for example, they won't be able to follow their recipients' spending throughout the ledger, even if they have a view of it. So we've met these tumblers now, and they're the places where you send the money and hope for it to be forwarded on. But what does it mean for a tumbler to be trustless? Because just relying on them completely in exchange for hopefully getting some anonymity doesn't seem the best solution. So we want to achieve like certain properties. One of them is theft prevention, which means that this tumbler can't run away with the money or send it to a place where you don't want it to go. And then the next one is availability, which means that if the tumbler in some ways has enforcements to prevent it from stealing the money, maybe it can still make it unspendable, so it would just be frozen in some place, which is obviously also not ideal. So comparing the solutions that exist, the naive solution which we introduced with the bath achieves anonymity only modulo the trusting the tumbler itself, because this person gets sent the money and the addresses and they see where the money originally came from, so they know this mapping very obviously. And so if you can, for example, query that person, then you can reveal those links. Availability also modulo the tumbler, because they can go offline indefinitely and then your money would be frozen. Theft prevention is also modulo the tumbler. So if they wish just to like spend that money for themselves, you've given them the ability to do that. But in terms of communication and like frictionlessness, this rates pretty highly. So off-chain communications is just one. So the recipient needs to tell the sender their Bitcoin address that they want to receive the money to, just like normal. And on-chain transactions, this is two. So the sender needs to send the money to the tumbler, and then the tumbler forwards it on. which is really good. So then the next solution is Tumblebit, which was introduced in 2017 and uses RSA puzzles to allow the sender and receiver to interact with a central server off-chain in a way that money can transfer from the sender to the receiver in a way that not even the off-chain Tumblr lands the mapping. So in this case, under some specific conditions, anonymity is achieved for all parties in question. Availability is still modulo the server. Like if they run away forever and never come back and don't want to interact anymore, then the money, the transactions just can't go through. But theft prevention in this case is guaranteed. But they pay for this in terms of communication. So off-chain, there are 12 interactions in total between like sender, Tumblr, and recipient, and combinations of those three. And on-chain communications, this is 4, which can get expensive. So the next solution is CoinJoin, which we were introduced to in the last talk also. And in this way, what people do is broadcast their intention to spend some coins, but they wish to do so in an anonymous way, with enhanced anonymity. So they meet people off-chain in some way, and instead of sending a transaction which is signed, which is just from their single sender address to their single recipient's address, they make a combined transaction, which is to all of the intended from all of the intended sender addresses to all of the intended recipients. And then they pass this around and they all sign it. So availability is modulo the senders in this case, because if a person broadcasts their intention to create a transaction and then decides halfway through the transaction they no longer want to go through that and refuses to sign, then you have an availability problem. But once those signatures are completed, then the transaction will go through. So theft prevention is not an issue due to like properties of digital signatures, but in terms of off-chain communication, you really pay for this. You need to like meet these people who you've never met before in some way. You need to coordinate all of these transactions. You will need to be online at the same time to do these things. But on-chain transaction-wise, this is great. Then the next decentralized solution is Exim, which was introduced in 2014. It again receives anonymity for the senders, but they learn their recipient addresses. Availability is great, and the design of this protocol was such that it would require no off-chain communication. And they do this by communicating only on the Bitcoin blockchain, and they use it almost as a bulletin board. But in terms of, and they pay for this in terms of on-chain communication. So there's like 7 transactions that need to be done, and they need to be quite spread out. And so this is like an 11-hour process in total. So you can see the contrast between the more centralized solutions where there's a server sitting in between the sender and recipient, which pay for that in availability, and then the more decentralized solutions, which compromise in communications. In order to make up for these properties. So what we thought was, is this like an inherent thing? If you're doing a decentralized procedure, like do you need to pay for it in terms of communication? And what we found was that using Ethereum, you don't actually have to make this compromise at all. So in this case, we get recipient anonymity, so the senders have the guarantee that the intended receivers will be able to withdraw the money, but they don't learn which receiver is that specific receiver. Availability guaranteed by the Ethereum blockchain. Theft prevention is guaranteed by like the protocol itself. Off-chain communications is 2. The caveat is a positive one, because these 2 communications are a Diffie-Hellman key exchange, which then, if you want to repeatedly transact with the same people, you will never need to communicate with them off-chain again. You can just derive new keys and use the protocol in that way. And on-chain communications, it's 2, and again, it's like to a Tumblr, away from a Tumblr. So how do we achieve these properties? So the first thing that we use is Ethereum smart contracts and ring signatures. And if you don't know how ring signatures work, pretty much they, like a normal digital signature, has a public and private key combination, and your signature is produced by the private key verify against the public key. Ring signatures, you instead take a group of public keys, and signatures produced by either of the private keys verify against the whole group of public keys in a way that doesn't reveal which of the public keys your private key corresponds to. So the idea of Mobius is that the senders and receivers will communicate so that the senders have the public key of their intended recipients, and they'll deposit this key into a smart contract along with some agreed denomination of money. Then the next thing that happens will be, obviously, once the agreed upon number of senders have deposited money, so this is how you form your anonymity set, then the smart contract will be in this state with all of the keys in. Then the intended recipients can form these ring signatures over the set of public keys, and they can withdraw money in this way. So the way I've presented it here, however, has a slight issue in that if, for example, Dora was offline, then Bob could create this ring signature, and because of the properties of ring signatures, like unlinkability, he would be able to withdraw one coin, and then he would be able to withdraw the other one if Dora hadn't submitted her signature in time. And so what we do is we use linkable ring signatures, so we keep track of the signatures that have already been seen. And linkable ring signatures have this additional property that even though you still can't identify which public key, private key, which public key the private key that the signature was formed with corresponds to, there's like a deterministic tag that is associated with the signature, and every signature that Bob will produce will have this same tag. And so if we keep the signature in the smart contract, then Bob can't produce more than one signature, he can't withdraw more than once. And so you have this guarantee that every sender will have exactly their recipient withdraw exactly the money that they sent them. Then in terms of communication, because sending back and forth keys every time is like something which you don't have to do if you use, for example, fiat, we wanted to produce an optimization which allowed people to have the same, if you have transacted with someone once, you can transact with them again without having to do all of this communication. And so we use this concept that's called stealth addresses, or in this case we use the stealth keys. And the stealth keys, how they work is that the recipients will have long-term public keys, but these won't be the keys that are deposited into the smart contract. Instead, keys will be derived by the sender in this deterministic way so that the receiver will be able to derive the corresponding private keys every time without having to interact. And if you're interested, this is how they're constructed from the master public keys, which would be the receiver's long-term known public keys. And in this way, between contracts, like if you transact on one day and another, you're not linked, but you don't have to do that additional communication. So we implemented this. It's pretty extremely reasonable. So the deposit transaction takes pretty much no time at all to create, is like not very much more expensive than a plain Ethereum transaction, and the withdrawal transaction takes like a little longer, but still only on the scale of milliseconds, and is, we think, extremely reasonable in terms of like real life cost. Then here is the comparison again to conclude. So we've introduced Mobius, which achieves like great things in terms of availability and theft prevention, but then without compromising on the communication, which hopefully will encourage people to mix more often. And that's all. Thanks.
Thanks, interesting work. In your table, if you just go back one, I just had a question about what is the availability problem with CoinJoin?
Oh, so it's just if during the construction of the transaction, and then also like when you're all signing the transaction and passing it around, and when you're collecting all of those signatures, if any person decides not to sign, you have to start from the beginning again.
But you don't lose the coins.
Right, exactly. So
Okay.
no, yeah, exactly. It's just an inconvenience thing. That's
Okay.
it, yeah.
Okay.
Any more questions? Thank you, Rebecca.
Thanks.
So to deliver the final
coiners is what we call bin mixins. So you might have an attacker that has information, for example, about your timing, and so if the attacker has very specific timing information, then it might be useful to, whenever you choose a coin, you not only choose this one coin, but a group of coins that are up against these strong attackers, and you can find more information. So does this actually matter? Was anyone actually using Monero at that point for privacy-sensitive transactions? Not all transactions that happened in the network might be equally privacy-sensitive, right? So our goal here is to quantify different usage types. So the first interesting thing that I want to point out here in the graph of the number of transactions is this dip here in early 2016, when seemingly the number of transactions on the network was cut. And this was right when Monero doubled the block interval. So in cryptocurrencies, every few minutes, a so-called entity, the miner, will create a block that will bundle a number of transactions, and they have to solve a computational puzzle for that. And as a reward, they can get some coins. Now, these coins are delivered in a special Coinbase transaction. So when you go from 1 minute to 2 minutes for these blocks, you basically have half the amount of Coinbase transactions, which means that probably a lot of these transactions here were only related to mining. Now, many people, if they mine, they organize in mining pools because it's so computationally intensive. So they will all work for this pool, the pool will get the money, and the pool will at some point in time distribute the money out to the miners. Now, looking at the mining pools, what we found is that many mining pools actually announce the payout transactions on their websites. Well, this is a privacy hazard, because if you can link the block that a pool found to the payout transaction that you can found, this could enable simply the same kind of deducibility that I've shown you before, because the reference that is probably the real one is the one linking to the block that this pool found. But this data being available also means that we can look at how much transactions are actually related to mining activity, and this is what we did. We crawled the website sites of a large number of mining pools, the number of blocks they found, number of payout transactions. Then we estimated that in addition to the Coinbase transactions, around 0.44 transactions per block are related to mining, mostly in form of these payout transactions. So if we subtract this from the number of all transactions, we find that indeed in 2015, early 2016, normal transactions, but starting mid-2016, early 2017, we see I showed you this spike before. This is right where both of them started accepting Monero. Quite a bit in this exchange rate. And so we were interested in trying to figure out how many of these transactions are actually related to Alpha Bay. So Carlos Oscar and Nicholas Christine for the rest of these transactions, we have to assume that there are potentially other privacy-sensitive transactions. So this study was yet another example of what Stephen already mentioned earlier. Cryptocurrency privacy inherits really the worst of the field of data anonymization, where the blockchain is public, and once you expose these weaknesses, it can be exploited retroactively. So all these users who transacted back in 2016, 2017 are potentially vulnerable to de-anonymization. And it inherits from communication anonymity that the behavior of some users can have an influence on the anonymity of others, which you saw in the example of the deducibility attack, where the choice of some users to not include any mixins had a negative effect on the anonymity of other users. So in summary, we identified and quantified these two weaknesses in Monero's mixin selection. Many privacy-sensitive transactions in 2016-2017 are vulnerable to de-anonymization. We estimate that this are more than 1,000 transactions per day in late 2016, especially if those are used for example, darknet markets that might be criminal offenses that take years to expire at all. So these users are potentially at the risk of de-anonymization by law enforcement agencies. That being said, clearly these illicit businesses tend to be early adopters of new technologies, but are also always or often the most visible. But there are many legitimate uses that are less visible and that are also similarly affected. Thank you.
Thanks for your talk. So you said, so the mix-ins, as you said, have to be the same denomination.
Right.
But when you showed the that table of how much the miners paid out to each person, like they had 6 significant figures of accuracy and they were all basically random. So if are those divided into like standard size coins? How do you?
Yes, they used to do that. They now switch to a completely new format where they hide the values. So basically everything appears as 0 values, so you can just select any coin. But back then the client would split the outputs in certain denominations.
Great. And I had one other question. On one of your slides you said 0.44 transactions per block were mining related?
In addition to the Coinbase, that are these payout transactions. So when a pool pays out the money to the actual participants in the mining pool, they might do that every few blocks. So you don't have
So that's very few, but on your graph, if you just go back to that slide, yeah. So
this is reducing both the Coinbase transaction and this additional 0.44 transactions per block. And this is aggregated on a daily basis. So you have 1 block every 2 minutes.
yeah, and you have
So
like how many transactions are typically in a block?
So the Coinbase transaction alone is like 1,400 transactions per day, right?
Yeah.
Why we see this first drop and then the second drop and then these additional 0.44 transactions.
Okay, so most
reduce it
blocks are
further.
basically empty.
In the first days, yes.
Yeah, okay, thank you.
Any further questions? We have a lot of time.
Hi, I was wondering if you considered repeated behavior over time. Let's say that I'm a vendor at one of these markets, so assuming the market is an intermediary, they're regularly sending me my money. And at one transaction, maybe I can't tell if I got it from AlphaBay or not, but after 10 transactions and AlphaBay is in every single one of my 4 mixins or whatever, it's pretty clear that I'm regularly receiving money from them. So I'm wondering, did you look at these kinds of repeated behaviors over time? Or do you think that this could work if you didn't?
So repeating behavior is a bit more difficult than, for example, in Bitcoin, because Monero also uses stealth addresses. So it's hard to cluster, so you can't cluster addresses, which makes it a lot harder to infer that certain or multiple transactions that look unrelated are actually to the same person or from the same person.
Any other questions? So thank you, Malte. We now have a break until 11:30, and then another great session will follow.
And the 3 speakers in the next session come up and see me right now. Thank you.
Prova micro Faristol. Hola, 1, 2, 3. Des d'aquí? Prova, 1, 2, 3. Provant micro. 1, 2, 3.
before we start, I just wanted to remind you that if you want to go on a hike and you're still a maybe, you have to turn that into a yes by lunchtime today. Okay? Who do you tell? Hands up if you were the one to tell, or if you know who it is. Yeah, the registration people out there. Oh. No, exactly. The remote people, they can hike remotely. Yeah. All right. Okay, welcome to the next session, which is the crypto session, which, notwithstanding the topic of the last session, I remind you crypto means cryptography. So we have three great speakers today. So our first speaker is Giulio Malavolta, who will tell us about functional credentials.
Hi, thank you for the introduction. So today I'm going to talk about functional credentials. Can you hear me well? And so this is a joint work with Dominic Deuber, Matteo Maffei, Max Rabkin, Dominic Schroeder, and Mark Sinkin. Let me give you a brief introduction about classical authentication mechanisms. I hope you're all familiar with it. Normally, like this is better. Sorry. So classical authentication mechanism exploits several features of the carrier, which might be the possession of a token, knowledge of a secret, or some unique physical features. Now, this has obvious problems, which is a very well-known topic in the literature. It's the fact that the verifier, whenever a naive authentication mechanism is used, can just track the user and can just uniquely identify it based on his credential if this mechanism is executed in a naive way. So it has been apparent from so many years of research that we need two properties at least of authentication mechanism, which are the soundness. Soundness means that the prover cannot fool the verifier into accepting some capabilities that doesn't have, and anonymity, which means that beyond the output of the protocol, the verifier should not learn any additional information about the carrier of the credential. So let me give you a very quick introduction on how anonymous credential works. So we establish a common ground of notation. Typically, users request their credential token, which in this case is a key, to an authority, to an issuer, and based on a certain set of credentials. In this case, the guy is male and greater than 18, and he gets the appropriate credential. And later on, he can interact with a certain verifier and convince that he satisfies a certain policy, whether this policy could be male or greater than 18, in such a way that the verifier does not learn anything but the fact that the prover satisfies this policy, and he can do that thanks to the token of the issuer. Now consider the following scenario. Let's take a data owner that outsources a database for a cloud service, and he wants to outsource also the management of the data set, and of course he wants to give selective access to his data to certain clients. So he entrusts the cloud to make access control on his behalf. Okay. So whenever users comes in, of course the credentials are distributed to appropriate users. So whenever users comes in, he can prove to the cloud that he's entitled to write an entry if he satisfies a certain policy. In this case, he needs to be greater than 18. But this has certain privacy concerns. For example, in this example, one thing that the cloud may ask is, even though it doesn't know anything about the carrier of the credential, why does this guy needs to be greater than 18? So what's in this data, right? So this itself is an information that gives a non-trivial leakage to the cloud, which we don't want. And ideally, we encrypt data because we don't want to reveal anything about the cloud. And the fact that we put a certain policy associated to a certain data, it gives already some information, right? And to convince you that this scenario is meaningful, I give you a concrete example where this is actually a concern. If you consider Oblivious RAM intuitively wants to hide the access pattern to the eyes of the database, in the sense that whether you write on an entry X or on an entry Y should be indistinguishable to the eye of the cloud. In this case, if you want to perform access control over this data, this leakage is unacceptable. So it's in inherent conflict with obliviousness. So we need a different solution for that. So that's why we formalized the notion of functional credentials, which we believe to be the good solution for this problem. And in this work, we formalized the security definition. We proposed a generic construction that uses predicate encryption in a black box way. For those of you who are familiar with that, it means that you do not assume any specific instantiation, but you take any scheme and it just works right out of the box. You don't have any expensive step on it. Just only the code that is used for this primitive is run. So if, for example, running a zero knowledge proof over that is not allowed if you want to have a black box instantiation. And we implement this. Unfortunately, we don't have a full-fledged implementation for any possible function, but we have to restrict ourselves to constant depth Boolean formulas, and you'll see why in a second. So let me give you a quick overview about the notation of functional credentials. The scheme is relatively simple. We define a setup algorithm which is run by the issuer, a grant credentials which is run by the issuer again and takes as input the master secret key, and this is used to grant a certain credential given a set of attributes A. Now the key difference with respect to classic and anonymous credentials is the presence of this delegate algorithm, which does not delegate a credential, but instead delegates a token which is used to check against credentials. So you can see this as a token where the policy is embedded inside this token. You can test it against several credentials, but beyond the output of the protocol, you should not learn any information of the policy which is embedded in this token. And so the first protocol is the classical anonymous authentication, whereas the second protocol has the key difference that uses indeed the delegation token and on the verifier side. So you can think this as a blind verification of credential. So the verifier does not really know what it's checking, but he makes sure that the issuer, sorry, that the carrier satisfies the policy which is encoded in this token. So what are the properties that we want to make sure, that we want to ensure? So the first is unforgeability, which is also I also mentioned it as soundness. Is the fact that a carrier which does not satisfy a certain policy should not be able to fool the verifier. In this case, this Hello Kitty should not be able to prove that she is male and greater than 18. Anonymity says that two provers which are not, for which the protocol returns the same output, should not be able to, you should not be able to distinguish among them efficiently. And finally, the most important properties of this work is policy hiding. Policy hiding says that if I give you a certain token, you should not be able to tell what's the policy embedded in this token beyond what is trivially leaked by the protocols that you run on them. Of course, the verifier that possesses this token, he can test it against credential. This is a functionality requirement. but beyond the output of this protocol, you should not learn anything about the policy that is embedded in this token. Okay, so what's the main tool? What's the main tool to construct a functional credential? So the main tool that we use is predicate encryption, and predicate encryption is a very powerful cryptographic primitive, which is characterized by the following algorithms. So again, there is a setup, and you can see already the similarity here. There is a key generation that takes a set of attributes and returns a key for these attributes. There is an encryption that takes a message and a policy and encrypts this message against this policy. And okay, I skip forward to the decryption. So you are able to decrypt a certain ciphertext if the policy associated with the ciphertext matches the attributes associated with the key, which is P of A equal 1. Also, we need to additionally assume that this predicate encryption supports a re-randomization algorithm. This is more of an algebraic property of the scheme, but it is satisfied by most of the instances that we know. So predicate encryption for inner products was introduced by Katsahai and Waters in 2008, and a breakthrough result by Garg et al. Proposed a functional credential, a predicate encryption for any function, but it's very slow and from non-well understood assumptions, so it's very hard to implement. I think we're not at the point in time where we can implement this scheme yet. Okay, so how does our construction work on a high level? My objective here is to give you a high level intuition of the construction. And if you're interested in more details, I refer you to the papers. Again, there is an issuer. The issuer as a set of public parameters, which in this case are the public key and the secret key of our predicate encryption scheme. And a credential consists, for a set of attributes A, consists of a key under the secret key of the issuer, whereas a token consists of an encryption of a given policy of 1. In this case, it can be any fixed string, but in this case, we take 1 for simplicity. So it's not really important what you encrypt there. What's important is the fact that you embed the policy there. Okay. So let's take a look how we verify. So the challenge here is, so the approach becomes relatively easy once you throw non-interactive zero knowledge to it. But the challenge here is that we don't want to do that because that makes things usually way less efficient. So we want a black box construction in the predicate encryption scheme. How much time do I have left? 4 minutes, perfect. So give you a quick intuition what's going on. So recall that the prover holds a key, whereas a verifier holds a ciphertext. And the main idea of this protocol is that if the prover satisfies the policy, it should be able to decrypt any ciphertext, right? So first thing that the two parties do is to run a coin tossing protocol with a certain random coin, which are denoted by the dices. Then the verifier takes as input this randomness, re-randomizes the encryption of the message, and sends it to the prover. The prover then tries to decrypt it, commits to its result, and at this point in time, the verifier does not learn anything about the prover. And in order to avoid selective failures attack, the verifier has to send the coins output by the coin tossing protocol. With this information, the prover can recompute the old protocol above, and then if everything went well, he decommits, but thereby revealing the answer to the challenge. And if the two messages match, then we can be sure that the prover had enough rights to access the policy. Okay. So we actually implemented this. We have a C++ prototype implementation, and we use the predicate encryption of Okamoto and Takashima from CANS 2011. And so you must know that there is a generic transformation from inner product to Boolean formulas of constant depth. And so the main parameter of our analysis is going to be the size of the array. Unfortunately, the depth of the formula the length of the array grows exponentially with the depth of the formulas, and this is why we have only constant depth. It would be amazing, of course, if you could push this result, but I think that would require a major breakthrough in crypto, as since these two notion of functional credential and predicate encryption, they're very entangled. And of course, if you have better ideas, I'm really happy to hear them. Anyway, so let's believe that the vector n is a good measurement for the moment. Of course, commitment is done in the random oracle model, so we use just a hash function for the sake of efficiency, and so those are essentially for free. So you can see that for a vector length of around 1,000, the running time of the prover and verifier are still in the realm of feasibility, so it means seconds. So which is that's something. It's not ideal, but at least it's a feasibility result. And interestingly enough, if we apply our functional credential scheme to oblivious RAM, then we eliminate the need for some expensive zero knowledge, which were from the original scheme. And if you compare the running time of the two authentication mechanisms in terms of number of clients, there is at least one order of magnitude of improvement in that. So that's the main take-home message of the table. And so we didn't go any further 10 clients, because that's as far as the original paper goes, but we expect that the gap will increase together with the number of clients. So it seems like our solution here scales significantly better than that. Okay, so with that, I would like to conclude, and thank you for your attention, and I'm happy to take questions.
Questions for Giulio?
Thanks for your talk. So a little clarification on sort of the threat model. So you say that the verifier that has been delegated the policy should not be able to learn much about this policy, right? But it seems to me that if this verifier is colluding with some possible users that have been giving a credential, it can actually figure out relatively quickly what that policy is. Is that correct? Or
so what you're saying is that given a certain set of keys, you can just test your thing against that. Yeah, but yes, that you can always do, and we can't prevent that because that's part of the functionality of the scheme. But the idea is that you should not learn anything beyond that. And again, a scenario where this is useful could be when the policy is not like a Boolean policy, but it's a more complicated one. So, for example, oblivious RAM.
More questions?
In your definition of anonymity, do you consider unlinkability between two sessions from the same user?
Say again. Sorry.
So, in your definition of anonymity, if the same user has two different sessions, can those be linked, or that's not covered?
Oh yeah. So we just gave it a unified name, but so if you go in the paper, the definition is model giving Oracle access. So you can query this object as many times as you want, and you should still, even if you query it many times, which means two sessions, you should still not be able to figure out who is who.
More questions? I have one. So these times here are in milliseconds, so that's nice and fast. But your previous slide had like 15 to 20 seconds.
Yeah. So
what's the difference between these?
Here the vector length is 10.
It's very
So
short. Okay.
it's very short. If you see they are
Near
consistent.
2,000.
Yeah. So again, we didn't push it far because the original paper just considered up to 10 clients, so we couldn't compare with it. But you can see it as roughly 1 client per n. So it's still again in the realm of feasibility for let's say 1,000 clients.
Great. Any last questions? All right, let's thank the speaker. Okay. We avoid technical problems by using the same laptop all 3 times. We avoid one particular class of technical problems. All right, our next speaker is
So I suspect most of you have seen this idea of nested encryption in the context of onion routing. A client multiply encrypts a message that it wants to push through this onion routing network, and then each layer of the onion router strips away one, each onion router strips away one layer of encryption, and the plain text message, perhaps something you're trying to send off to some server, emerges at the edge of the onion routing network. The problem that we ask in this paper is what exactly is the problem that this nested encryption is presumably a solution to? And I suppose the presumably is the operative word here, because I think until you have formalized this in a meaningful way, you don't really know whether or not nested encryption works, or what properties the encryption scheme needs to satisfy in order for nested encryption to do what you hope that it would do. So we seek here a provable security treatment for this problem, and I'm doing this in the kind of concrete, practice-oriented tradition. So I want a clear syntax and definition for the problem at hand. And once that's done, we want to look at some constructions. I'll explain that Tor's relay protocol doesn't satisfy our definition. It doesn't for the simple reason that tagging attacks are excluded by our definition of security, and Tor's relay protocol is susceptible to them. And then I'll describe an alternative solution that does satisfy the definition, and it's effectively Nick Matheson's design 1 from proposal 202 from the Tor community. Okay, so when I say I want to give a provable security treatment here, I want it to be concrete and self-contained. In particular, I'm not looking for something in the UC, in the universal composability model, but something that's clear and game-based. It'll be based on indistinguishability. This is the basic problem an adversary faces when it's interacting with one of 2 kinds of oracles, and it just wants to identify which of the 2 oracles it's interacting with based on the input-output behavior of those oracles. Indistinguishability is one, and in fact the most popular way that we use to quantify advantage, the adversary's advantage in distinguishing these 2 oracles. It's just the probability it says 1 when it interacts with one world, minus the probability it outputs 1 when interacting in the other. Perhaps the main idea here is simply to view the problem that nested encryption aims to solve as a flavor of authenticated encryption. Authenticated encryption is by now a very well-known primitive in which you're trying to simultaneously achieve privacy and authenticity. That is ostensibly what's going on in these protocols. The Tor relay protocol, for example, adds in a bunch of 0 bits and then applies nested encryption based on counter mode. It would, at the endpoint, we check for the presence of those 0 bits. That's the authenticity check, and the nested counter mode is presumably our mechanism for achieving privacy. So who's doing the encryption and who's doing the decryption here? So the encryption is effectively the client, A in this picture, and decryption is then done by each and every node, each and every onion router. There are already lots of flavors of authenticated encryption, probabilistic authenticated encryption, non-spaced, misuse resistant, robust, all kinds of flavors. And I'm suggesting that the problem that nested encryption solves is yet another flavor of authenticated encryption, and we call it onion authenticated encryption, onion AE. Okay, so I promised approvable security treatment of this problem that I've now named, onion AE. So I like to clearly separate the syntax of the thing that we're trying to define from the security definition. So what is this thing just as a simple syntactic object? So it's a three-tuple of algorithms. There's a key generation algorithm, an encryption algorithm, and a decryption algorithm. The key generation algorithm produces the vector of everybody's keys. So the client here, presumably his key consists of the collection of all of the individual OR's keys, though that's not actually mandated. And he does the encryption. The decryption is then done in phases, one layer at each OR. Unlike conventional non-spaced authenticated encryption, we're going to need that the encryption algorithm as well as the decryption algorithms are stateful. The strong security notion we're after is not going to be achievable by stateless schemes, and we'll see that later. You know, after we define the syntax of any cryptographic object, we normally specify the correctness condition for it. And I want to do that quite explicitly here, and we'll see why later. Correctness is simply asserting that no matter what key you choose over here, no matter what sequence of messages you feed to the encrypting party, if you faithfully relay the ciphertexts through our OR network, you'll get back, well, m equals m prime for each message. You'll get back the sequence of messages that you initially encrypted. You'll never get back this distinguished symbol bottom, which is used to indicate an authenticity error. Okay, so that's the syntax, and how then do we formalize security? So it looks rather like non-spaced authenticated encryption or almost any of the other AE flavors. Our adversary here is imagined to be interacting in one of two worlds. On the left is the kind of real world where it has an actual encryption and decryption pair of oracles. The encryption oracle is doing something like that nested encryption operation, and the decryption oracle, well, it's emulating what happens at a particular OR. So the adversary identifies which OR in the chain that it's targeting, that's this index I, and then the ciphertext that it's feeding it, and it gets back whatever the algorithm dictates should be returned. This is the real world. We would like this to be indistinguishable from an ideal world whose behavior is very simple. Whatever you ask to encrypt, it produces random bits. Whatever you ask to decrypt, well, usually it produces random bits too. But at the very edge of the network, at the nth OR, we're going to assume a fixed length sequence of ORs, at the very end, it would produce, instead of random bits, the indication of a failure, of invalidity. This is a kind of utopian definition in the sense that if you stopped there, you could easily distinguish the real and the ideal worlds. This is typical when we do indistinguishability-based definitions, that we have to add in some extra little bells and whistles to effectively forbid the trivial wins, to ensure that the adversary doesn't get credit for them. What makes this setting unusual, I think, compared to other authenticated encryption goals, is that it's annoyingly difficult to describe just what it is that those trivial wins are. Okay? And that's because we have this whole chain of ORs, and each of them is maintaining state. And there are kind of obvious attacks, but putting down formally what those obvious attacks are and excluding all and only them is really unpleasant. The idea that we pursue here is to automatically exclude the trivial wins. And when I say automatically, I mean you exclude all and only the wins which are unavoidable by virtue of the correctness condition. I just described to you the correctness condition. So usually correctness only plays a role for saying, you know, what's the functionality of your protocol. You know, if you decrypt something you've encrypted, you have to get back what you started with. It's a functional requirement. But here now, I'm going to use correctness as an integral part of giving the security definition. The basic paradigm is that you give a utopian game, like the one depicted here, that is not achievable due to the correctness condition. And you effectively factor out those wins that are unavoidable by formalizing the correctness condition and automatically adjusting the game accordingly. And this idea is, which logically precedes this paper on onion encryption. Unfortunately, it's published just after. That'll appear in a separate paper at Crypto in a couple of weeks. So we call this idea indistinguishability up to correctness. And we start off with our indistinguishability game, the adversary trying to distinguish some real from some ideal game, with indistinguishability defined in the normal way. And we modify it by automatically silencing all of those queries that we somehow are obliged to do something about because of correctness. When exactly do you silence? Silence means instead of answering this yi value, we answer some distinguished value that says, I'm not saying. You silence when for every scheme pi in the class of correct schemes, the response is the same. It's determined by the transcript that's already gone of communication between the adversary and that oracle. The adversary's been having a conversation with the oracle. If at some point in time what the oracle answers is that which it's obliged to answer by virtue of correctness, then instead of answering as you would like to, you replace that response by some distinguished value, I'm not saying. That's the idea. Here then is the utopian game for onion authenticated encryption. This is the full form with all the silly details, like ensuring that you set up the key before you start encrypting and decrypting. And this is everything. It, together with the correctness condition, then serves as an input to that oracle silencing idea, and out pops your definition. What would this look like without the oracle silencing? So in some sense, we're kind of lucky because there was independent work going on we recently learned about, presented at Eurocrypt a couple months ago by De Gabriel and Martijn Stam. And they set out to solve essentially the same problem. They wanted a game-based formulation of the problem that nested encryption solves. And I've clipped the games from their paper. This looks pretty bad, but this is only the beginning. There are the rest of them. Okay. So I believe this seemingly simple idea really helps to radically simplify the games you're trying to understand when the context gets, just a little bit more complicated, something like onion authenticated encryption. Oh, seems to have a little out of order. There's a bunch of limitations I want to acknowledge right off. What I've described so far only includes the outbound messages. You need to add in more stuff to take care of inbound messages coming in over the same onion routing network. I haven't included the possibility of corrupted ORs. That seems very strange because, of course, onion routing is largely about ensuring that you maintain privacy despite some subset of the onion routers being corrupt. We haven't included in our modeling this leaky pipe idea that appears in Tor, where sometimes the length of the sequence of ORs you're passing through is 3 and sometimes it's 4 or something like that. Okay? It always has fixed length in our treatment. And then I think the most interesting branch, the most interesting choice we had to make, was that we check all of our authenticity at the time of exit, when you're just about to leave the network. This is the same choice that was made in Tor's relay protocol, but it's not the only possible choice. You could instead have said, once a message gets inserted into this onion routing network that's wrong, you should stop it at your first opportunity. It shouldn't traverse the network. These two different flavors of onion routing can both be formalized in this Oracle silencing paradigm, though in the PETS paper we only formalize the time of exit formulation. I don't really know which one is better, and I think it's an important question that, you know, those doing concrete onion routing have to face as to which flavor of onion routing they're after. I'll mention that once you add in the extra layer of encryption that effectively goes on, you know, by the TLS record layer, you're not actually getting, you know, in Tor something like this time of exit authenticity checking. You actually are getting the stronger form, apparently, of authenticity checking associated to eager authenticity. Just a little bit on constructions. As I said, Tor's relay protocol doesn't satisfy our definition, and it doesn't for the simple reason that tagging attacks are excluded by this strong definition of security. You know, quite informally, tagging attacks are a consequence of using a malleable encryption scheme, and authenticated encryption is invariably stronger than non-malleability as a requirement. It implies non-malleability. We do have a construction, as I mentioned, and it consists of nested encryption. But the kind of thing that you're nesting is not a conventional symmetric encryption scheme. It's not something like counter mode. You need a much more powerful primitive. Here, what we're using is a wide block pseudo-random permutation, a wide block cipher, and it has to be tweakable, in fact, which means that there's this additional parameter which impacts the behavior of the wide block cipher as though it were a separate key. So we do the nested encryption, having added in redundancy, you check it at the edge of the network, and then you tweak according to the ciphertexts that have been output so far at each layer in the OR. Okay, just a few take-homes. I want to emphasize that there's importantly these two different variants of Onion AE, whether you're checking at the very edge or constantly as you traverse the network. I think that's an important axis of comparison that hasn't been discussed much. There's a much more recent proposal than the one that we've analyzed, proposal 295. We've looked at it quite recently, and I can't tell you whether it does or doesn't satisfy this definition of Onion AE. It's not at all obvious. And you know, finally, I'll ask whether any of this actually matters for a construction like Tor. And I guess my answer would be to ask a Tor person whether the tagging attacks matter. This seems to be something that hasn't been entirely closed on within that community. From my point of view, it's really nice when you build your protocols from primitives that have some kind of understood security property. And here, you know, we're trying to get to what understood security property nested encryption might have if you implement it well.
Speaker. Questions for Phil, or does anyone from Tor want to answer that last question? Staring at some Tor people, other Tor people, Nick.
Sorry for being so far away from the logical place for a microphone. I think this is a kind of question that we can only really figure out in dialogue with cryptographers like you, because we sort of know what we want from an engineering point of view. The big trade-off on replacing the relay crypto is performance. If there were a widely believed to be strong, definitely, and definitely fast white block cipher that we could, tweakable white block cipher that we could drop in, then we would love to use it. Most of the ones we've seen seem to have performance problems on one platform or another, but we haven't tested out everything.
Yeah, so I'll mention that one of the problems with this scheme I've suggested is that this object E is really not a standard cryptographic primitive. This is the complete set of constructions that I know that have been offered for it, and I don't know that any of them are particularly mature or efficient.
Other questions? Okay, I'll throw one. So I really like the Oracle silencing trick, so that's cool. But I have a question. So in the Oracle silencing trick, you basically, in the real world, you check whether the output would be the same for all queries, for all transcripts up till that point for all correct protocols. And I'm worried, might it be possible that the adversary could construct a sequence of queries for which, say, the fifth output would always be the same, but there's no way to know that yet, right? Because the real world might only be able to learn that later, and so it couldn't output the silence symbol.
So the silencing, as I've described it here, is defined in this very existential way, and that would seem to be a problem. That can it even compute whether or not this thing should be silenced? And something I glossed over is that in order for this notion to be meaningful, you need to check that the silencing actually is computable, that function can be efficiently computed. And in order to accomplish this, you typically have to recharacterize when silencing happens, and you end up with a complicated game nonetheless. So this serves as a kind of simple descriptive language for the definition, but you're not done, unfortunately, at that point. To really do anything productive, you'll have to check computability, you'll have to worry about things like whether or not transcripts are arising, in the ideal game, which could never arise in the real one.
Great, thanks. Oh, pass the mic back.
I was wondering if you tried to find a definition that was kind of the weakest that would provide what somebody might want out of nested encryption. And if you were willing to satisfy a stronger definition, could you do it with a more standard, more widely available construction? Like, for example, why not just nest standard authenticated encryption?
So in answer to the last question, why not nest standard authenticated encryption? This would cause a length increase with each hop, and we kind of took it as a requirement that we wanted the ciphertext to stay constant length regardless of the number of hops you went through. The other part of the question, whether or not one might have done better in terms of efficient constructability of schemes if you targeted a somewhat weaker goal, that's certainly possible. Nonetheless, the space between, you probably really want non-malleability and authenticity. We don't, even in the conventional symmetric encryption setting, have interesting examples that sit between there. You can construct artificial examples that are, in that space, but we don't know how to achieve like non-malleable symmetric encryption any more efficiently than authenticated encryption. And my guess is that there's not a big gap there in terms of the efficient constructability of schemes. If you do try and target non-malleability as your basic goal and not authenticity, I believe you'll end up with a much more complicated definition than overshooting and trying for authenticated encryption's counterpart.
Okay, I'm afraid we're out of time, so let's thank the speaker again. Okay, and the last speaker of this session is Uptake Encryption, who will be talking to us about dynamic searchable encryption.
Hello everyone, I'm Uptake Encryption from Koç University, and this is joint work with Mohammed, Babis, and Dave. So our setting is the outsourced storage setting, where for the sake of confidentiality we encrypt our data, but then how do we provide search functionality? So this trivial protocol can provide search functionality. The client encrypts his files, outsources them to the cloud, and then to search, he downloads all his files again, decrypts them, and performs a local search. This will be trivially and obviously secure, but unfortunately extremely inefficient. So what we want is a balance between security and efficiency, and we are interested in index-based searchable encryption solutions. In this setting, we have our files and a dictionary of keywords, and for each keyword, we have a set of files, actually file identifiers, file names if you wish to think, that contain this keyword. Now what we are going to do is we will generate a key associated with this keyword, and this is usually done through a pseudorandom function, and we will encrypt this list with this key. Then we will store this list at, let's say, random locations in our index and outsource this encrypted index together with the encrypted files to the server. So here the client will generate three things: the encrypted files, the encrypted index, and some metadata. The client will keep the metadata locally and outsource the encrypted index together with the encrypted files to the server. To perform a search, the client will generate a token associated with the keyword, send this token to the server. Now this token will enable the server to perform a search over the encrypted index, but only learn the files associated with this keyword. When the server learns those, sends the encrypted files, so now the client can decrypt them. Now what you can observe here is that there is a leakage. We are leaking information to the server. What are we leaking? We are leaking what's called the access pattern, essentially the list of files that are associated, that contain this keyword. Unfortunately, we need to leak this if we want the scheme to be efficient, because we want the server to send us only the related files so that our download is efficient. But notice that here, it doesn't mean that the server knows the keyword or the files. It is done in a way hiding the actual keyword and the contents of the files. They are encrypted, but it only learns the association between them. There is also another leakage called the search pattern, essentially the number of times a keyword is searched for. And this again leaks in many searchable encryption schemes because these tokens the client generates are deterministic. For dynamic schemes, as in our case, we want to be able to add or remove files, there is further leakage. And without forward privacy, what leaks during a file insertion is that the file identifier and file size, of course, the number of keywords in the file, and whether or not these keywords were previously searched for. And why does this happen? With a search, the client is sending this token, which is essentially the key associated with this keyword. And then now we are adding a new file, let's say that contains a keyword that was previously searched for. This token enables the server to link this new file with the old searched keyword. And of course, in the worst case, if all the keywords were previously searched for, then the server knows all these associations. Such leakages in searchable encryption schemes may lead to many attacks: access pattern attacks, search pattern attacks, file injection attacks, etc. And as we said, without forward privacy, each new file can be linked by the server to previous searches for free, essentially. But the good news is that forward privacy prevents this kind of leakage. And this helps prevent some of these mentioned attacks. So with forward privacy, when we insert a file, we leak the number, the file identifier, the file size, and the number of keywords in the file, but we no longer leak any association with this new file and any previously searched keyword. So our scheme achieves forward privacy roughly as follows. So as usual, the client generates a token revealing this associated key with a keyword to the server. The server, as usual, performs its search over the encrypted index, finds the associated files, and returns to the client. Now, in addition, the server also deletes these entries that were accessed. And then the client reinserts these entries with a fresh new key at new random locations in the encrypted index. So on the slides, I will only mention an honest but curious setting, and we will use some non-constant but small client storage. In the paper, we have a dynamic, efficient, parallelizable forward private scheme whose security is proven via simulation. So I will demonstrate our scheme using an example. Let's say we have 3 files. File 1 has 3 keywords. File 2 and 3 contain 2 keywords each. So as you can observe, our dictionary is of size 4 unique keywords. And I will use this notation WIFJ to denote that file J contains keyword I. So let's say file 1 contains keyword 4. I will denote it with W4, comma, F1. We will employ 2 indices. One at the client side keeps for each keyword the number of files associated with that keyword and the number of searches we have performed over that keyword. So these are 2 simple integer counters, nothing cryptographic here. And at the server side, we have a dictionary, let's say a hash map. Now, initially the client can build this index locally and then finally outsource it to the server. So the client will take each file, and for each keyword in the file, it will start with incrementing the counter, and then it will generate the key associated with this keyword. Then it will create a pseudorandom address to store this association of W1 and F1, keyword 1 and file 1, and encrypt this entry with, again, a key derived for this particular entry. So I will show you the unencrypted version of this index, but everything in this index is encrypted. Okay? So the client will switch to the next keyword in the file, increment its counter, create the key associated with this keyword, find the pseudorandom address to store the association of W3 and F1, encrypt it, and store at the index. And the client continues, encrypts and stores W4 F1 association at some other pseudorandom location, and continues with other files, and finishes completing this encrypted index. Now, together with the encrypted files, the client can outsource this encrypted index, and now we are ready to perform a search. So to search for, let's say, keyword 4, the client will generate the key associated with keyword 4, and simply copy this counter and then send these values to the server. Now the server, for each file associated with this keyword, so the counter was 2, so the server will do this twice, it will find the locations and decryption keys for the entries in its index. So it will compute the address, find this location, compute the decryption key, decrypt the entry, and learn that this keyword is associated with file 1. Then it will go to the next entry, find its location and decrypt, and learn it's also associated with file 3. So the query result is file 1 and file 3. The client, the server will just send these values to the client for the client to decrypt. Then the server removes these entries that were used. Okay, simply removes them. Now the client increments its own local counter for the number of searches performed for keyword 4, and then this enables him to derive a fresh new key. With this fresh key, the client will compute Naive pseudorandom addresses and naive encryption keys to encrypt these two associations and store them back at the server's index at naive random locations. Now to insert a file, let's say which contains two keywords, 3 and 4, the client will again create the keys associated with these keywords, prepare these associations of keyword 3 and file 4, keyword 4 and file 4, encrypt them with these naive pseudorandom keys, find their pseudorandom addresses, and then send these to the server for the server to store them. Observe that at any point in time, the server's index only has entries that were encrypted with a key that was never revealed to the server. So for example, keyword 3, we never searched for it, so the server never received a token for it. Keyword 4, we searched for it, the server has a token for keyword 4. But this entry, remember we generated a fresh key for keyword 4, so now this entry is encrypted with a fresh key that was never revealed to the server. Finally, the client simply increments its counters and we are done with insertion. To perform deletion, we need to add another index. So at the server side, we will have this right-hand side index as additional. This index will simply keep, again, this index will be encrypted. It will simply keep for each file the addresses on our left-hand side index for entries that are related to this file. That's it. And at the client side, we will keep another set of counters. So for each file, how many keywords are associated with this file. To delete a file, let's say file 3, the client generates the key associated with this file for this right-hand side index of the server, and then simply copies the counter and sends these values to the server. Now the server computes these addresses on the right-hand side index, decrypts them, learns the addresses on the left-hand side index, and now simply deletes these entries, and of course the file. The client also simply deletes its entry, the counter in its index. So at the client side, we have this left-hand side counters for search and insertion operations, and right-hand side counters for insertion and deletion operations. So until our work, there were only two schemes providing forward privacy. One was using an oblivious RAM type of structure, so it was having some polylogarithmic overhead, and the other was using public key operations. So here we have forward privacy together with parallelism and achieving essentially optimal asymptotic complexity with only simple symmetric primitives. We also measured the concrete performance of our scheme with a data set containing roughly 4 million files, roughly 10 million keywords, and 500 million total index size. So 500 million keyword file associations. We implemented this and tested on an Amazon server with multiple cores, but our main tests were using only a single core and compared against the previous work, Sophos. So I will only show one graph for the sake of time here. We have further graphs in the paper. This is the search performance, and this is per entry, per keyword file association. Our scheme with a single core, the red line, takes roughly 10 microseconds per association, and the blue line is our scheme with 5 cores running in parallel, which takes only roughly 3 microseconds. So more than 3 times speed up with 5 cores. So in conclusion, what we see is that forward privacy is a very important feature for searchable encryption schemes trying to resist some of these attacks. And our scheme achieves forward privacy. It is parallelizable. It is efficient. So we only employ pseudorandom functions, hash functions, and at the server side, a simple hash map data structure. And we have a security proof via simulation. As future work, there are 2 main issues. One is backward privacy. So remember, forward privacy removes the linkage between a new file that is inserted and previous searches, can we remove the linkage between a deleted file and later searches? Unfortunately, existing solutions are not efficient. And remember I said we have this client storage for these counters. So for each file and for each keyword, we need to store these values. In the paper, we say you can use Oblivious RAM to outsource this storage, but it adds a new round of communication. Can you reduce storage without adding new rounds of communication? Thank you for listening, and I will be happy to answer your questions.
Questions? Okay, I'll start. Oh, is there one over there? Great.
Would you get anything stronger if you sort of, instead of having just one counter, if you sort of preloaded the server with some random selection of keys in the future? So, sort of guessed what queries would happen, and you preload the server with some things for those, so that you don't actually have to send, so that after you do a query, just the deletion happens, and you don't always have to repopulate. You've sometimes already done.
I see, something to maybe amortize some of the complexity, you mean, or? So let me, if I understood you correctly, first of all, in many searchable encryption schemes, because this started with static schemes, the description goes as follows. You have a build phase, a pre-computation, let's say, because you already have a set of files and that they contain keywords, so you build the index once and then upload it to the server. But for dynamic schemes, you may want to add a new file or remove a file during the process, so that's the problematic part. Now in our case, this reinsertion of fresh keys and new random locations doesn't affect the asymptotic complexity. So it introduces a round of communication but doesn't affect the overall asymptotic complexity.
Okay, I'll throw my question now. Can you go back to 44? Yeah, nope. Yeah,
Here?
great. But go to the last, no, that was the last frame of 44? No, go to the last, yeah, great. So when you do a deletion, it affects that right-hand table, but
Yes.
not the left-hand table. So,
Yes.
So the left-hand table is really overcounting the number of files for any keyword?
Exactly. So this, I don't know how visible is this. So here is the interesting part. So the optimal search cost would be OD, meaning D is the result set size. So you are only spending time and returning the files associated with that keyword. So now in terms of computation, the previous scheme, Sophos, has D plus number of additions and deletions. In our case, we have D plus number of deletions. So even though we deleted a file, the search should still go over up to the total number of files that were at some point associated with that keyword. So the server still spends that time. But for the deleted entries, the server will realize there's no valid entry there, so it's not included in the result.
But and is it the case that you get another benefit that when that search is complete, the server at least knows how many files actually match, and then when you do the when you recompute the new key for that keyword, do you only have to do the number of actual files that are left, or do you still have to?
Of course, so when you recompute, actually, you can do it because this number of deletions already leaked to the server. So we are not trying to hide it anymore.
Right. Any other questions? I have one more question, actually. So earlier on, you said that forward privacy defends against file insertion attacks.
So forward privacy prevents the leakage between a newly inserted file and a previously searched keyword.
Right, but there's the attack where the server gives a file to be inserted, right? Like say the database is email and the server just sends email to the client, right? So the server knows that this file that was just inserted has these keywords, and so when one is looked up, it knows, this is that, one of those keywords, right? So does your forward privacy technique stave off that attack?
So as far as I know, it doesn't fully eliminate.
Right, okay. That's what I thought. Okay, any last questions? Standing between you and lunch? Okay, let's thank the speaker again. Speakers of the next session go to Claudia, and just remember, if you have not confirmed that you're going on the hike with the registration people, now is the time.
I'm just going to test it.